the previous lecture, we talked about two different coordinate systems that we use to describe the motion of particle moving under the influence of a force. In this lecture, we start with how to solve the equation of motion when the particle is moving under constraints. So what we are going to talk about is the constrained motion. And I'll explain to you what we mean by that and how do we go about solving this. Suppose there is a particle that is moving under the influence of a force F, then its motion is described by equation of motion that is given as ma equals the applied force, where m is the mass of the particle and a is its acceleration. Written in terms of its coordinate, I can write this as m r double dot equals f, where double dot denotes second derivative with respect to time. Of course, if the particle is free to move, that means it can go anywhere. Then I solve this equation and get r as a function of time given a force. On the other hand, if I restrict its motion, and I'll talk in a minute about what I mean by restricting its motion, the motion can be quite different. For example, I could take a bead moving on a straight wire. And the bead can move only along this wire, and let us say this wire is in x direction. Then no matter what force I apply on this bead, the bead is going to move only along the x direction. Therefore, its motion is restricted. As another example, which is quite well known and also known as Atwoods Machine, is two masses moving on a pulley when they are tried by this string. In this case, the masses are no longer free to move. That means if I have this mass m1 and the other mass m2, m1's motion is not determined by this equation alone. That is, its motion is affected. This is not correct. Its motion is affected by the presence of the other mass. Similarly, motion of m2 is also affected by the presence of mass m1. And this constraint comes about because of this rope that keeps them moving together. These are two examples of constrained motion. And how to deal with this when the motion becomes quite complicated or number of masses increase or number of constraints increase is going to be the topic of discussion in today's lecture. So let us start with our first example, that is a mass or a bead moving on a straight wire. As I said, in x direction, let's say. Through this example, I would like to introduce terminologies that are going to be in use when we talk about constrained motion. So if I apply a force on this, what does the wire do? The wire applies a normal reaction on this body. Why does the wire apply a normal reaction on this body? Because it doesn't want it to move anywhere except along the wire. So it is this normal reaction N that is really restricting the motion of the particle along the wire. This is called the force of constraint. To recap it, I'll again say that the effect of this wire on this body, I'm making it slightly bigger now, is just to produce a force N or a force of constraint. If you look at this body, I have replaced the wire by this force of constraint. This is known as the free body diagram. of is a particle or a body under motion. So, what do we mean by free body diagram? By that I mean I will make the body by itself, nothing else, and represent all the forces applied externally or applied by the constraints on it, and that I will call free body diagram. Let us see how do I write the equations of motion for this body. Since the normal force is going to be perpendicular to the wire, so N is going to have only two components in y direction and in z direction, and x is always going to be 0. The force F that I have applied, or I should write a vector here, is going to have all three components Fx, Fy and Fz. With these components of the forces, the equations of motion of this particle are going to be mx double dot equals Fx because Nx is 0, my double dot equals Fy plus Ny, and mz double dot equals Fz plus Nz. These are three equations of motion that I get from F equals ma. Let us see how many number of variables there are. There are x, y, z, n, y and nz. 5 variables. On the other hand, I have only 3 equations. So, I have 3 equations and 5 variables. Obviously, with this I cannot solve the problem. Where do I get the 2 other equations from? And this is where I start thinking the 2 of these variables n, y and nz came because I imposed a constraint. So, the equations should also come from the constraints themselves, and that is precisely where they come from. The equations of constraints are that y is equal to 0 and z is also equal to 0, and this implies y dot or y double dot both are 0, and so is z dot and z double dot. So, I have 2 more equations, total 5 equations and 5 unknowns, and I can solve the problem. Let us now look at the second example of constrained motion that I considered earlier, and that was the Atwoods machine, in which 2 masses are tied on a string that is passing over a pulley that is massless and frictionless, and so is the string. So, let us write again. This is mass m1, this is mass m2, rope or the string is massless for simplicity, and pulley is massless as well as frictionless. You may have solved this problem time and again in your previous courses, but what I want to focus on here is how to really deal with it from the constrained motion point of view. And therefore, first thing I am going to do is see what is causing the constraint. The constraint is caused by this rope that forces the 2 masses to move together. What is the force of constraint here? The force of constraint that really makes the masses to move together is nothing but the tension in the rope. So, tension in the rope is the one that keeps these masses together. Next, if I were to make the free body diagram, for the 2 masses, let me remind you again what a free body diagram is. A free body diagram is where I replace the agency causing the constraint by the force of constraint that it applies. So, if I were to write make the free body diagram for mass m1, it will be something like this, that there is a force pulling it down, m1g, the gravitational force, and there is a tension T, which is the force of constraint pulling it up, and that is a free body diagram for mass m1. Similarly, I can make free body diagram for mass m2, that will also be similar, m2g pulling the body down and tension T pulling it up. You may ask me at this point, why did I keep the tension the same? The tension remains the same because the pulley is massless, frictionless, and the rope is also massless, and therefore it doesn't require any force to move them. And that is what I said earlier. I had taken massless rope, massless pulley and frictionless pulley to keep things simple, because I want to focus on the constraint part of it. Now let us write the equations of motion. If you recall from the previous slide, the m1g and m2g are acting down and T is acting up on both the bodies. So equation of motion is going to be m1 a1 in y direction is equal to T, which is pulling it up, minus m1g. m2 a2 in y direction is equal to T minus m2g. You may ask, I am writing a1 y, a2 y, which way is my y, and things like those. So let us be more precise. Let me measure my distances from the ground and be more precise, because that will also help me later to write my constraint equation. Let this be the ground. Let the distance of mass m1 be y1 from here. Let the distance of mass m2 be y2 from here. Let the center of this fixed pulley be at height h from the ground. And now I can write, this is tension T pulling it up, m1g pulling it down, tension T pulling it up, m2g pulling it down, and therefore I can write m1 y1 double dot is equal to T minus m1g. Notice that all the directions and everything is correct. I must take care of that because we are dealing with vector quantities, although I am writing this in one dimension. Similarly, m2 y2 double dot is going to be equal to T minus m2g. I have gotten my two equations of motion, but again the number of variables are y1, y2, t, 3. So one equation that is missing must be provided by the constraint itself, and that is where this picture comes in handy. Recall again, the constraint that the two masses move together is provided by the fact that the rope is of fixed length. And I can express this mathematically as this part, which is h minus y1, plus this part, which is h minus y2, plus this part is of constant length. Since this part is always of constant length, I can write my constraint equation as h minus y1 plus h minus y2 is equal to a constant, or shuffling terms around, I can write this as y1 plus y2 is equal to a constant. This is my third equation. To bring it to usable form, in the equations of motion I differentiate it and then get y1 dot plus y2 dot equals 0, and also y1 double dot plus y2 double dot is equal to 0. So let us write the equations once more. Again, I am solving this problem of two masses attached to a string which is passing over a fixed pulley. I have m1 y1 double dot equals T minus m1g, m2 y2 double dot equals T minus m2 g, and y1 double dot plus y2 double dot equals 0. I have 3 equations and 3 unknowns, and I can solve my problem. Notice this constraint equation just tells you that when one particle is moving up, the other one is going down. When one particle is accelerating up, the other part is accelerating down. Let us now solve these equations. Let us eliminate T first. So, for that I subtract equation 2 from equation 1. In doing so, I get m1 y1 double dot minus m2 y2 double dot is equal to m1 minus m1g plus m2g. Since I know that y1 double dot plus y2 double dot is equal to 0, this implies y1 double dot equals minus y2 double dot. If I substitute, I get m1 plus m2 y1 double dot equals m2 minus m1 g, or y1 double dot equals m2 minus m1 over m2 plus m1 g. A result you already know. If m2 is heavier than m1, then y1 double dot is up, and that is precisely what I am getting. You see, I did not make any assumption about m1 or m2 being lighter or heavier and things like those. The results automatically popped up. Through these 2 examples, what I have tried to demonstrate to you that constraints in a particle's or a body's motion can be caused either by external agencies, as we did in the case of a particle moving on a wire. The constraint was caused by this wire, or by other body itself. That is, in this case, this mass m1 and m2, when they were connected by this rope, this was providing the tension, but the presence of one mass restricted the motion of the other mass. And also, when we solved these 2 simple problems that you already knew the answers of, we also tried to develop stepwise strategies to solve motions of different bodies when they are moving under constraints. Let us try to write them. So, first step in solving a problem is going to be identify the constraints and forces of constraints. Once I have identified the constraints and forces of constraint, the second step is make free body diagram of all bodies, and these bodies, which are treated separately, are also called subsystems of the system. Let me remind you what a free body diagram is. When I make free body diagram for a body, I make that body freely and consider all the forces that are being applied from outside and the constraint forces on it. There may be more than one constraint force. and that is my free body diagram. The third step is going to be then write the equation of motion for each subsystem. At this stage, you will see that the number of variables in the problem is more than the number of equations that you have written, and therefore there are some missing equations, and these equations are going to be provided when you write the equations of constraints. There may be more than one. Still, if the equations don't match, either you have missed something or you have misformulated the problem. Go back and do it all over again, and once the equations and number of variables match, the last step is solve the problem. I am going to demonstrate this now with a slightly more complicated problem. It will be like Atwoods machine, but slightly more complicated. So what we are going to do is take two fixed pulleys, they are fixed at some height, pass a string of fixed length over them, and the string turns around with the help of this third pulley. So let me number them: pulley number 1, pulley number 2, which are fixed, pulley number 3, which can move up and down, and let me also attach a mass here, attach a mass here, attach a mass here. This is mass M1, this is mass M2, this is mass M3, and this is attached again by a rope. Call it rope 2, call this rope 1, and both are of fixed length. And what I want to do now is, when I release this system, how does the motion take place? For example, where does M1 move? What is its acceleration? Where does M2 move? What is its acceleration? How does M3 move? What is its acceleration? So we will go back to our steps, and the first thing we want to do is identify the constraints and forces of constraint. Let me make the figure again for you. The constraints are that the length of rope 1 is fixed. So constraints are rope 1, which is this one, has fixed length. Similarly, the other constraint is that rope 2, from which mass M3 is hanging, has fixed length, and I got to use them later in writing the constraint equation. Forces of constraint are tension T1 in rope 1 and tension T2 in rope 2. These are my forces of constraint. Let me show them again in the picture. This is my pulley, mass M1, here is the pulley, here is the other pulley, mass M2, M1, M3. Here the tension works this way: T1, T2. These are the forces of constraint. Again, I am assuming T1 and T2 to be the same, because I will be considering for simplicity massless and frictionless pulleys, and assume that all the ropes are massless. the next step in the game is make free body diagram for all moving parts. You can see that these two pulleys are fixed and therefore they are not going to move. This mass is going to move, this pulley is going to move, this mass is going to move, this mass is going to move, and therefore I'll have 4 equations of motion. For that, again, I take a reference point from which I'm going to measure my distances. To make that picture again, this is mass M1, pulley number 3, mass M2, mass M3. I'll measure the heights from the ground. Since these two pulleys are fixed, they are at height h, which is a constant from the ground. This distance, let it be y1 for mass M1, let it be y2 for mass M2, let it be y3 for mass M3, and let it be yp for the pulley, because I am considering all the subsystems of this whole thing which are moving. To write the equations of motion, let me again go back to the free body diagrams and I will take them up one by one. If I go to mass M1, it had tension T1 acting this way, mass M1G pulling it down, and its height is measured from the ground as y1, and therefore the equation of motion for this is going to be M1 y1 double dot equals T1 minus M1G. I can similarly write the equation of motion for mass M2, which is going to be M2 y2 double dot equal to T1 minus M2G. Same thing for M3, M3 y3 double dot is going to be equal to T2, because it's the tension in the second rope that is pulling it up, minus M3G. The fourth moving part is the pulley itself, and for that the forces pulling it up are T1 on both the sides and tension T2 in the middle. Since the mass of the pulley is 0, therefore I am going to have 2 T1 minus T2, which is the net force, that must be equal to 0. You see, I have gotten 4 equations of motion. So number of equations is 4. How about the number of variables? This is y1, y2, the heights of masses 1 and 2, y3, height of mass 3, yp, the height of the pulley, T1, tension in rope 1, and T2, tension in rope 2. Total number of variables is 6. As I had said earlier, at this stage when you write the equations, the number of equations are going to be less than the number of variables. The missing equations are provided by the equations of constraints, and that is what we got to write next. That should give us 2 equations of constraint, and that will make the number of equations to be 6, which is equal to the number of constraints. Let us do that. For that, again we go back to our diagram. Where I will now take the constraints into account, that the lengths of these ropes, both the ropes are the same, are fixed. So this is y3, these were at height h from the ground, this is at y2, this is at y1. So let us see what are different distances involved. This is going to be h minus y1, this is going to be h minus y2, or this is yp, I need that also. this is going to be h minus yp, and so is this. Therefore, the length of the rope is h minus y1 plus h minus yp, h minus y1 plus h minus yp plus another h minus yp plus h minus y2, and these distances are also fixed because the radius of pulley is fixed. So, this is going to be equal to a constant. In other words, I can write, if I reshuffle the variables, y1 plus y2 plus 2 yp equals a constant. To again bring them to usable form, I differentiate them and write y1 double dot plus y2 double dot plus 2 yp double dot equal to 0. That is one of the equations that I need. I have now gotten 5 equations. Sixth equation is very easy to get, realizing that the length of this rope is fixed, and therefore, yp minus y3 is constant, or yp dot minus y3 dot is 0, and so is yp double dot and y3 double dot. Basically, the pulley and the mass are moving up and down together. So, let me rewrite all the equations once more. I have now gotten 6 equations, and there are 6 variables in the problem. The equations are m1 y1 double dot is equal to t1 minus m1 g, m2 y2 double dot equals t1 minus m2 g, m3 y3 double dot equals t2 minus m3 g, 2 t1 minus t2 is equal to 0, y1 double dot plus y2 double dot plus 2 y pulley double dot equals 0, and y pulley double dot minus y3 double dot equal to 0. Equation 1, 2, 3, 4, 5, 6, and 6 variables. I can solve them and get my desired answer. I am not going to solve it for you here, but I will give you partial answer, and you can try to get that after solving these equations at home. The answer for y3 double dot comes out to be 4 m1 m2 minus m3 m1 plus m2 divided by 4 m1 m2 plus m3 m1 plus m2 g. Continuing with the same problem, I will change it slightly and give this as an exercise to you. Let me again attach 2 masses with a pulley, let it go like this, except that now I will attach a spring to this mass. I would like to set up the equations for this. I would like you to set up the equations for this and solve them using the methods that we have learnt so far. I will do 2 more examples of the methods that we have learnt to demonstrate how effectively we can solve problems using the method of making free body diagrams, taking subsystems, using constraints, constraint equations, and equations of motion. As an example, again let me take a block that is sliding on the surface of a drum which is fixed on the ground. The block starts from the top, slides down this way, and the problem that we ask is, at what angle does this drum at what angle does this block fly off the drum? The radius of the drum is r. I am choosing this particular problem because this will also give you some practice on using planar polar coordinates. So, to start with, again we identify what the constraints and forces of constraints are. So, constraint on the moving block here is that the radius r is a constant, and this is equal to the radius of the drum r. The force of constraint then obviously is the normal reaction that the drum applies on the block. Since the motion is circular, because before leaving the drum the block is moving in a circular path here, I am going to use planar polar coordinates, taking this angle as phi, increasing this way, and r obviously is the radius. My second job is to write the equations of, to make the free body diagram for the block. So, if I take the block here, the free body diagram that involves only the normal reaction or the force of constraint and the external force is going to be mg of the block acting downward and the normal reaction acting this way. And after making this free body diagram, I write the equations of motion for the block, except that this time I want to use planar polar coordinates. So, at this position the block is at distance r. Maybe I should go to the next page for this. The block I am taking to be here. So, at this position it is at distance r at an angle phi. This is the force mg acting this way, this is the normal reaction acting this way. Since this is phi, this angle is also phi, and therefore, in r direction, if I want to write the equation of motion, it is going to be m times the acceleration in the r direction, which if you recall from the previous lecture is r double dot minus r phi dot square, and this is going to be the force in r direction is n in the positive r direction, and since this angle is 90 minus phi minus m g sine of phi. Similarly, in phi direction the equation of motion is going to be m r phi double dot plus 2 r dot phi dot equals m g cosine phi, but with a minus sign because the force is acting in negative phi direction. Remember that phi is increasing this way and the component of mg is in this direction. So, the equations of motion that I have gotten are m r double dot minus r phi dot square is equal to n minus mg sine of phi, and m r phi double dot plus 2 r dot phi dot is equal to minus mg cosine of phi. These are two equations of motion, and number of variables involved are r, phi and n. As I had said earlier, at this stage the number of equations would generally be less than number of variables in the problem, and that is because so far I have not taken into account the equation of constraint, which in this case happens to be r is equal to r, which is a constant, and therefore r dot is equal to r double dot is equal to 0, and that is my third equation which I can solve. So now I am going to substitute third equation in number 1 and number 2 and solve the resulting equations to get my answers. When I do that, I get m r phi dot square with a minus sign in front is equal to n minus m g sine of phi, and the other equation comes out to be m r phi double dot is equal to minus m g cosine of phi. It is these two equations that are going to give me n, and rate of change of phi with respect to time, r anyway is fixed by third constraint equation. To solve this equation, I first solve the second equation, and I use a trick for this, because you see I cannot really integrate with respect to time. So I write phi double dot, which is the time derivative of phi dot, as time derivative of phi dot times d phi dt, using the chain rule for differentiation, and that gives me equals phi dot d over d phi as of phi dot, which is nothing but 1/2 d over d phi of phi dot square, and therefore my second equation now reads m r over 2 d over d phi dot square is equal to minus m g cosine of phi. M cancels, and therefore I have r phi dot square over 2 is equal to minus g cosine of phi d phi, and remember the particle is starting from the top, so that means it is starting from pi over 2 and coming up to some angle phi. This gives me this equal to g 1 minus sine of phi, and therefore the result that I have is r phi dot square is equal to 2g 1 minus sine of phi. I leave this as an exercise for you to show that this is equivalent to energy conservation, because the left hand side is related to the kinetic energy and right hand side is related to the change in potential energy. Using this, I can now solve equation 1 for the normal reaction. Recall that equation 1 is nothing but m r phi dot square, the minus sign here, is equal to n minus mg sine phi. I substitute for r phi dot square that I just derived, and I get minus m 2g 1 minus sine of phi is equal to n minus mg sine of phi, which gives me, after reshuffling, 3 mg sine of phi is equal to n plus 2 mg. This gives me the normal reaction as a function of phi. Recall that it is the normal reaction that is enforcing the constraint, that is, the particle moves with a constant radius. When it flies off the cylinder, at that point there is no contact between the block and the particle, and therefore when the block flies off the cylinder, at that point n would become 0, and therefore 3 mg sin phi at that point would become equal to 2 mg, which implies that at angle phi from the horizontal such that sin phi is 2/3, the block will go off the cylinder. This is one problem that I have solved using the steps that I have outlined and polar coordinates. Next, I am going to solve a problem that involves two particles and constraints on their motion due to their contact. In our next example, we take two bodies that are in contact and apply constraint on their motions because of that. For that, I am taking a wedge with an angle theta here, and there is a block that slides on it. The wedge has mass m, this block has mass small m, and all the surfaces are frictionless. Therefore, this wedge is free to move in this direction and the block is free to move along the inclined plane. This is a constrained motion because the block of mass small m is free to move only along the incline. Therefore, its y and x displacements are going to be related. Let us see then what are the constraints. Constraints of the motion are that this block of mass m moves only along the incline of the wedge, and the other constraint is that the wedge moves only in horizontal direction. So, let us see what the forces of constraints are going to be. Obviously, the force between these two is the normal reaction on the block, let me call it N1, and the force that keeps the wedge on the ground is the normal reaction on it N2. The next step in our strategy is to make free body diagrams for all the moving parts of the system. There are clearly two subsystems here, one the block here, the other the wedge here. For the block, the free body diagram would give a force N1 acting in this direction and its own weight pulling it down. I remind you once more that the free body diagram means I isolate the system and represent all the constraints by the forces of constraint. The free body diagram for the wedge is going to be, by Newton's third law, of force N1 in this direction, its own weight mg pulling it down, and the normal reaction N2 by the ground. I would like you to notice that I have not involved the mass small mg in making the free body diagram of the wedge. That is because it is taken care of by normal reaction N1. After making free body diagrams, I am going to write the equations of motion. To write my equations of motion, let me first fix my coordinate system, and for that what I am going to do is make the wedge here. This is the block. For convenience, I'll choose this point to represent the coordinates for the wedge. Let this be x1, y1. Notice, since I'm putting this constraint that the wedge moves only in the horizontal direction, I'm explicitly writing y1, and later I'm going to eliminate this using the constraint equation, so that this distance right now is x1. Similarly, the coordinates for the mass m, let them be x2, y2, so that this distance is x2 and this distance is y2. Looking at the free body diagram, where mass small m has a normal reaction like this angle is theta, and a force mg pulling it down. If this angle is theta, this angle is going to be theta, and therefore I'm going to have the equation of motion as m x2 double dot is equal to n sine theta. That's it. And similarly, for the y coordinate, I'm going to have, this is my equation number 1, m y2 double dot is equal to n cosine of theta minus mg. That's my equation number 2. Third and fourth equations are going to be for the wedge. For the wedge, the forces are n1 in this direction, with this angle being theta, capital Mg in this direction, and n2 in this direction. So the equations are going to be m x1 double dot is equal to minus n sine of theta, equation number 3, and m y1 double dot is going to be equal to minus n cosine of theta minus mg plus n2, equation number 4. I have 4 equations and 6 variables, which are x1, y1, x2, y2, n1 and n2. As expected, because I have not yet taken the constraints into account, the remaining 2 equations are given rise to by the constraint equations. What are the constraint equations? The constraint equations are given by, let's draw this again and we will see. This is theta, this is the block, this is y2, this is x2, this is x1. Number 1, that the wedge moves only in horizontal plane, and therefore y1 is always 0, and therefore y1 dot is equal to y2, or y1 double dot is equal to 0. That's my equation number 5. And the block always moves on this inclined plane, and that means y2 divided by this distance, which is x1 minus x2, is fixed, is equal to tangent of theta, and therefore y2 is equal to x1 minus x2 tangent of theta, or y2 double dot is equal to x1 double dot minus x2 double dot tangent of theta. That's my equation number 6. I now have 6 equations and 6 variables, and I can solve the equations. I'll solve it again partially to get the value of n1 and rest follows very easily. Let me rewrite the equations once more. So, all the equations are m x2 double dot is equal to n1 sin theta, m y2 double dot is equal to n1 cosine of theta minus mg, m x1 dot is equal to minus n1 sine of theta, equation number 3, m y1, sorry, this was x1 double dot, y1 double dot is equal to minus n1 cosine of theta minus mg plus n2, equation number 4. Then y1 double dot is equal to 0, equation number 5, and y2 double dot is equal to x1 double dot minus x2 double dot tangent of theta, equation number 6. So, now I have 6 equations and 6 unknowns which can be solved very easily. These two equations together really give you nothing new but that n2 is equal to n1 cosine of theta plus mg, which tells you that n2 balances all the vertical forces acting on the wedge. The other equations, when substituted for, would give you a result for n1. I will leave the solution and substitution and all those things for you, give you the final answer, which gives you n1 is equal to mg cosine of theta divided by 1 plus m over m sine square theta. Once I know n1, which is a constant quantity here, I can calculate all the other quantities, x1 double dot, x2 double dot, y2 double dot, and their integrated forms, the velocities and the displacements easily. That brings us to the conclusion of this lecture, in which through simple examples we saw how we take constraints into account when writing equations of motion and solving for them in cases where the motion is not completely free. It can be restricted either by external constraints or by 2 or 3 moving particles themselves that impose restrictions on the motion of each other.